this is our definition of torque, and from here we take z component, z axis is along the axis of rotation, and then we write our dynamics for that fixed axis rotation, that torque z component is moment of inertia times angular acceleration. Okay. Now, let us do some algebra on this. Let us say, just look at one particle of the rigid body. On that particle there will be some force, internal force, external force, and for that particle there will be some position vector r vector, so r cross f, and for that particle f is dp dt, right? Correct? F is for a particle, force is just this dp dt, and you can write this as ddt of r cross p. Can I write that? As a function of time, this r vector can change. Particle can go here and there, and therefore this r can change. Can I write this equation? Can I take that r into d dt when r is a function of time? But if you have d dt of two functions, both are depending on time, u into v, u depends on time, v depends on time. What is this? If it is only this, I cannot write this equal to this. I cannot take this u inside here and say it is d dt of uv, right? I should not do that. But here I am doing precisely that. It is dp dt, and here it is r. R is also a function of time. Now it is a vector r I am writing. So if when it is rotating, it is changing, okay? But still it is allowed. See why? Expand this according to this one. D dt of r cross p will be equal to r cross dp dt plus p dr dt cross p. Differentiate one, keep the other intact. Differentiate the other one and keep the first one intact. I should not change the order because cross product is not commutative. Therefore, I have written in both the terms r is on left, p is on right. What is this? 0. Why? The angle between the two is 0. This p, this dr dt is velocity, and p is mass into velocity, and cross product of two parallel vectors is 0. So this is 0. Therefore, this d dt of r cross p is same as r cross dp dt. Okay. Now this quantity r cross p, this we write as, we give another symbol L. L is r cross p. Definition, not law. We call this quantity r cross p L, and the name of this is angular momentum. Of the particle about the origin. First time when you define something, keep track of the entire sentence, entire language. R cross p is angular momentum. If you remember only this one, it will not suffice. It is angular momentum of the particle. Which particle? Whose position vector is r, whose linear momentum at this instant is p. So of that particle. But even that is not sufficient. About the origin, if you choose your origin somewhere else, the same particle, the same linear momentum, the angular momentum will be different. Same velocity, same mass, everything same. I am only changing the origin. Of course, I have the choice. I can choose my origin anywhere I like. So I change the origin, then the angular momentum will be different. So keep track of all these things. Okay. So I have torque. Now if this is for particle, each particle. Now for the whole body, for that object, total torque. Total torque. This was at the particle, at one particle. Now I am writing total torque. That will be equal to ddt of total L. And what is that total L? It is nothing but summation over Li. Each particle of the rigid body, its angular momentum defined by that r cross p for that particle, all these individual angular momenta added together vectorially is the angular momentum of that rigid body. So for each particle I have defined angular momentum. How? The position vector of that particle cross product with linear momentum, mass times velocity of that particle. And then for all these particles which are in motion due to the rotation of the rigid body, I calculate Li, add them vectorially, remember it is a vector quantity, and that is the angular momentum of this entire rigid body. And the equation says that the total torque of all internal external forces is equal to ddt of that total angular momentum. And the sum of all internal torques, that will again become 0. Let me show you how. Just take two particles of the rigid body, particle number 1 and particle number 2. And here is the origin. So this is R1 and then you have R2. And internal force, this second particle exerts a force on this first particle, say attraction, molecular attraction, interparticle attraction. Then this will, one will attract 2 in this direction. Is this a action reaction pair? Particle 1 is attracting particle 2, particle 2 is attracting particle 1. Do these two forces make action reaction pair? No. Why? Okay, they should be in contact, then it, okay. This is because of the word reaction for the contact force. That is why I avoid that reaction I told you. Contact is not necessary. If two particles or two objects exert forces on each other, that on each other is the most important part. No third thing should come into picture. No third particle, third object, nothing from outside should come into picture. If you have two particles, they exert forces on each other. That pair of forces is action reaction pair. They are equal in magnitude, opposite in direction, and they act along the line joining these two particles. These are true in most of the situations of dynamics that we do, but they are not always true. Okay, they are not always true. If you have electric and magnetic interactions, if these charged particles are moving, and because of their motion of charged particles you have magnetic field, and through that there is a force q v cross b and all those things, for those forces this will not work. So just caution. But for most of the situations where we are not dealing with all those electric magnetic fields and especially the charged particles in motion, this does work. Gravitation, electrostatic force, then these contact forces, in this friction, tension, this will work. If you have two particles exerting forces on each other, the two forces will have equal magnitude, opposite direction, and they will be along the line joining the two particles. So if so this is F, let us say this is F and this is also F, but let me write it F2, or let me write this is F and this is minus F. Correct? One is F this side, one is F this side, so F and minus F. Now the torque will be R1 cross F1, plus R2 cross F2. I am only adding the internal ones. So R1 cross F minus, can you see these size of letter? So it is cross F. Your F2 is just minus F, right? So it is R1 minus R2 and cross F. What is the direction of R1 minus R2? Here is R1 vector, here is R2 vector. What is R1 minus R2 vector? It is this vector. Okay. So this R1 minus R2 vector and this F vector, they are parallel to each other, and therefore the cross product is 0. So all these internal torques will become 0, pairwise they will be 0. So when you add on all particles, all torques, all those pairs will occur, internal torques, they will be 0. So our equation becomes this equation here, torque is dl dt. Torque external is equal to dl dt. You only have to see the external forces, those interparticle, intermolecular forces, you don't worry, their torque will go away. Only the external forces on that rigid body will be dl dt, rate of change of angular momentum. And from here comes, if the external force is 0, external torque is 0, what happens? Angular momentum remains constant. If external torque is 0, dl dt is 0, dl dt is 0 means L is independent of time. So that is known as, what should it be known? Conservation of, law of conservation of angular momentum. You had law of conservation of linear momentum. If the total external force on a group of particles is 0, and rigid body is also a group of particles, special group of particles where the distances between pairs of particles are not changing, any group of particle, if the total external force is 0, its linear momentum will be conserved or constant, independent of time. That is law of conservation of linear momentum. And here is law of conservation of angular momentum. If the total external torque on the rigid body is 0, then the total angular momentum of that body will remain constant. That is conservation of angular momentum. Okay. Now let us practice few examples of rotational equilibrium. That means about no axis it is rotating, it is just in equilibrium. And equilibrium, I will take rest, at rest, this whole rigid body is at rest, or it is in pure translation. So let us focus on bodies at rest. So let us take certain examples. Let us take this door once again. I am not pushing, I am not applying any force, it is at rest, it is in rotational equilibrium. Therefore, the total external torque on this door should be 0. Correct? There is no axis of rotation, etc. It is not rotating. So you take any axis, any line about that, the external torque should be 0, or any point, take in vector itself, take any origin, and with that origin calculate what is the total external torque. Should be 0, there is no angular acceleration, it is in rotational equilibrium. Now tell me, just look at the door, what are the forces on this door as of now? So this is the door, these are the hinges, this is that center. What are the external forces on this? External means apart from the interparticle forces of the door. Forget those things. Apart from that, gravitation, weight, So I can write that weight from here. You know that the weight is distributed all over, but I can write a single mg from here, from the center of mass. What does it mean? That center of mass is defined in that way, that if you draw a single mg from that point, the torque calculation will not go wrong. You take all individual particles of the door, m1g, m2g, m3g, m4g, m100g, m billion g, and trillion g, everything. And for all those forces, you calculate the torque about some origin. R1 cross m1g, R2 cross m2g, R3 cross m3g, and all that. Sum that. And then take the single capital mg at the center of mass and just R cross that single mg. The center of mass is defined in such a way that these two must be equal. That's the definition of center of mass. Okay. So that weight is, I can take here. What else? From hinges. From these hinges you can have some forces, right? So let me draw components. From this hinge there can be a vertical force, let us see, F1, okay, let me write F1, fine, and then there can be a horizontal force, F2, okay. From this hinge also you can have a vertical force, F3, and a horizontal force, F4. Right. Now look at the vertical equilibrium. First look at the vertical equilibrium. The door is not going up, the door is not going down. So total force in the vertical direction should be 0. So let us take that. Upward force is F1 and F3, so F1 plus F3. Downward force is mg. So what should I write? F1 plus F3 equal to mg. Okay, not needed. And the door is not going towards right, the door is not going towards left. So the total force in the horizontal should also be 0. What does that mean? In horizontal direction, what are the forces? There are some other forces also. Wait. Yes, where are those forces? Where do I write? Ha. Okay. Ha. Repeat.
There will be some other forces in the direction opposite to F2 and F4.
Who will exert that force? The force has to be exerted by some object.
The door will exert the force
On the door itself.
on the hinge.
But I am not concerned about the hinge. I am not talking of equilibrium of hinge. Let hinge take care of itself. I am taking care of the door. So what force is acting on hinge? What is hinge doing? I am not concerned. I am talking of door only.
Gas exerts force on everything that it comes in contact with. So there's atmospheric pressure from this side, and from the other side there's atmospheric pressure.
All right. Good. This door is in contact with atmosphere on one side and on the other side. So there are external forces. This atmosphere is indeed external to the door. And the atmospheric pressures are equal on the two sides. It's equally distributed also. Right. So you will have forces. Now you are talking of perpendicular to this plane, right? Perpendicular to this door. From this side there is atmospheric pressure which is exerting force. On that side it is exerting force. They are equal, correct? And therefore when I am talking of total horizontal force should be 0, those two are already 0, correct? They are external forces, but then those two are adding to 0. It's uniformly distributed from the two sides, magnitude, so they are already adding to 0. Yes. Yeah. I have already removed, did not I? Let me do that. Let me do that. Okay, no friction. All right? And this is equilibrium. Total torque should be 0, total force should be 0. Ha.
Force between the locking pin and the hinge in the door, which is holding the door upright, connecting it to the hinge. F1, F4, which is
By?
Normal
that's
reaction.
why that's what it is. It'll be in equilibrium. There has to be a counter force on the other side for it to be in equilibrium.
But if there is a counter force, there should be an object which is exerting that force.
The door is exerting a force back on the hinges.
Right, but I am not concerned with the hinges.
Onto the framework there.
I am not concerned with that. What happens to hinge is not of my job. I am taking care of the door only at this moment. I can also analyze what happens to the hinge, but at this moment I am writing all the forces only on the door. I am looking at the equilibrium of the door. The total force on the door should be 0. The total horizontal force on the door should be 0. Total vertical force on the door should be 0. Total perpendicular z direction should be 0. Total torque on the door should be 0. The single point agenda in my charter is door. What happens to the earth? Earth is exerting a force on mg on the door. So door is exerting a force mg on the earth. I am not concerned with that. I don't care what happens to the earth. Okay. Similarly, if the door is exerting force on the hinge or that plate or that pane, whatever, I am least concerned about that. What happens to the door?
So if there's an inward force pointing to the door, there has to be an opposite force in the door as well.
But then if there is an opposite force, there should be a source of that. Someone has to exert that. You cannot get money in your pocket without earning it. Somebody must have given it to you. And if you have not shown that in your income tax return, you will be charged. It is true, if you are wearing very expensive specs, it means that you have a lot of money in your pocket. But there the story doesn't end. Then the question is, from where you got that money? So, okay, it is in equilibrium, therefore there must be an opposite force to make the total force 0. This is the first part. I am wearing a very expensive spec, so I must have a lot of money. But the other part is from where that money is coming. From where? Who has given rise to that force, that opposite force? Where is the source of that? That has to be filed.
So when the hinges apply a force on the door, F2 and F4,
Huh?
as the door is stationary right now,
Right.
the particles of the door must be applying an opposite and equal force.
On hinges. I don't mind. Let them apply.
So the reason for all this confusion is this action-reaction pair equation.
Okay.
When we talk about force on the door, we are talking on the door, not what the door exerts.
Right.
It has to be in equilibrium somehow.
Correct.
How?
How? That's what my question is.
There is a force that the hinges will exert on the door because the door is upright and standing, but that force is in 0 because the angle is in the same plane, which is why the door is in equilibrium, because even if you forget the reaction force, the total action on the door will be 0 because that theta is 0.
Yeah.
But the hinges will still exert that horizontal component,
Forces by the hinges on the door
but in the other plane also, so won't they be like the
perpendicular.
yeah.
Okay. Then the same question will be there. Who is balancing that? You are adding to your complications. This F2 and F4 are in the plane of the door. They cannot be balanced by a force perpendicular to the door. Right? So if you are also saying that hinge can also exert a force perpendicular to the door, you are only adding to the complication. Huh?
Force exerted by the other end, like that end, normal reaction force,
Where?
like that end.
Which end?
Like so, this side is the hinges, the other side.
Next to the handle.
Come. Yeah. Which side you are talking of?
That side, sir.
Here?
Yeah.
Here only
Normal
at
reaction force, like
by?
because from
By. That force that you are talking by what object?
by that end.
By which end?
That.
That's part of the door. Okay, I am only talking about the external forces. The total external torque should be 0. Total external force should be 0. But the wall and hinges I am not concerned, I am concerned with the door. Hinge exerts force on the wall, wall exerts force on the hinge, let them do whatever they are doing. Focus on the door.
F1 and F2 and F4 would produce torque in opposite direction.
First tell me how it is equilibrium in that horizontal direction, why the door is not going this way, why the door is not going that way.
F4 would produce a some rotational rotation around the center of the door, which would cancel out the that produced by F2.
Okay.
So like it would be in equilibrium.
No, that's fine. That's the rotational equilibrium. I am first talking of your simple translation. Total force should also be 0 in all directions. In this direction, let me call it x direction. Let me call it x direction. The total force on the x direction will be equal to mass of the door into acceleration in the x direction. Okay? Of center of mass. F is for a group of particles, total external force is equal to total mass into acceleration of center of mass. So this is true for all directions. So in x direction, total external force will be equal to mass of the door multiplied by acceleration of the center of mass in the x direction. Now if this total force in x direction is not 0, the center of mass should start accelerating in x direction. Your door will come out of the hinge. Okay.
So, but see, if you look at it from the other side, why is the hinge applying a force on the door in the first place?
Okay.
So, if we can look at it from the other side also, why is the hinge applying it?
So let us assume that hinge is not applying any force on the door. That means I can simply, gently remove the hinge, because it's not applying any force on the door. I can just simply remove it, and the door should still stay there.
So when you try to remove the hinge, when you try to remove the door, then you're exerting a force, and then the hinge exerts this reaction. The reaction happens when you exert the force in the first place. So right now, when you're not exerting a force, there is no hinge reaction either.
There is no hinge reaction. So F2 and F4 are 0.
Both are 0.
Okay, good. So F2 and F4 are 0. And what about F1 and F3? What about F1 and F3? They are there, or that is also 0?
Sure.
No, they just balance out.
They are there. Okay. So F2 is 0. Let us take that. So now it's very good. In x direction, no force, 0 force, no problem. In z direction, the total F1 plus F3 is equal to mg, so it is in equilibrium. In y direction, there are no forces, so it's translational equilibrium. Now let me take torque about this point. Torque about this point. Total torque must be 0, right? Total torque, external torque has to be 0. There is no rotational acceleration, no angular acceleration. What is the torque of F1 about this point? R cross F, remember. 0, right? This force acts here, this is R vector and this is F vector. R cross F is 0. What is the torque of this F3 here? 0. What is the torque of this mg? 0, about this point. This distance is, let us say, some x, mg into x. What direction? Torque direction. This is R vector and this is F vector, so R cross F going into it. Y direction. Total external torque is not 0, but the angular acceleration is 0. It is in rotational equilibrium. How can that happen? Very simple. Okay, very simple. This F4 is here and this F2 is here. And F2 is equal to F4. So total force in x direction is 0. Total force in z direction is 0. And now you can calculate the torque.
So, but if F2 is pointing that way, that means the door is exerting a force on the hinge.
Yes, it is. But I am not concerned with the hinge, but yes, it is. It is. It has to. Hinge is needed there. You cannot remove the hinge. That means hinge is applying force on the door. And then the door is also applying on the force on the hinge. I never said that it is not applying. I am only saying that I am not concerned with what is happening to the hinge. It is applying, definitely it is applying. Hinge is applying a force on that wooden frame, and so on and so forth. Now, F2 is equal to F4. So that takes care of my translational equilibrium. And rotation, now look at the, so this is by mg, and what about this F2? This is F2 is in this direction and R is in this direction. So it is F2 into R, this let me call it H, F2 into H, and this was inside, so this was minus and this is plus. What about this F4? R vector is in this direction, this is the position vector. R is in this direction, F is in this direction, R cross F, anti-clockwise, so towards me. So this is again F4 H j cap. There is a very good chance it can be 0. It only says that mgx should be equal to 2 times F2H. Remember, F2 is equal to F4. Okay. So you know how much will be this F2. This F2 will be mgx by 2h. mghx, everything is determined by the construction of the door. Weight of the door, x is the half the width of the door, and h is the height of the hinge from that central point. So all these things are determined, and that determines what is F2 and what is F4. And the direction has to be this way. Don't invert the direction, otherwise torque will add. Here you see the torque is in minus y direction for mg and plus y direction for these F2 and F4. So it can be balanced. If you put F2 in this direction and F4 in this direction, you will be lost. There is another way which you can understand qualitatively. If the hinge is not there, or hinge is there but it is not exerting proper forces, some screw has gone loose. So this door will try to, because of this mg, the door will try to turn. From this side it will try to turn clockwise. As it turns clockwise, it will push the lower portion of the wall or lower portion of the hinge with much greater force inside. See, it is rotating this way, and this is coming out, and this is going in. So it is going to push that wall, the lower one, and therefore the wall should push it in the forward direction. That is the direction of F4. Okay. The other part is coming out, other part of the door is coming out, and the hinge is saying no, don't go. Right? Suppose the hinge forces have become very weak, 0, etc. It's just somehow it's there. So what will mg do? This mg will try to rotate the door this way. That means this upper part of the door is going away from the wall. And it is hinge which is holding it there. So hinge is pulling it. That's the direction of F2. And lower, this door is pushing the wall because it's trying to get into the wall. And the wall says that no, don't crack me. So the wall is pushing it away. That is the direction of F4. It must be that way. And that will make everything simple, clean, torque is 0, force is 0 in all directions and all that. Yes?
I didn't understand why mg was minus and the other two were plus.
Okay, good. Say the torque is R cross F. the torque is R cross F. Now for mg, what is this R? This R is the position vector of the point where you are applying the force. So for this force, here is the point where this force is applied, and this is the origin. So this is the R vector. So R vector is in plus x direction. So this is the direction of R vector. The force vector is downward. Now if you do R cross F, this is R and this is F, R cross F, that vector cross product vector will be inside the board. Correct. Right?
I was saying that because mg is parallel to the axis,
Correct.
won't that torque sort of be nullified?
Yes. It is not going to have any effect on the rotation about this axis. So this mg has no wish, no will to rotate the door this way. Correct? So if your rotation axis is this vertical line, yes, this mg will not cause any kind of rotation about this, but it does want to rotate it about this axis. It wants to topple my door. Correct? This mg and is trying to, so it is about this axis, it will try. Okay? So you will have a torque in this direction, and that is what is coming. And why minus? Because this is R vector, this is F vector, and R cross F is going inside. Right? So if I take this as the, which should Z, X and Y, yeah, our Y should be inside, this should be plus and this should be minus. Doesn't make difference to my final thing, but the convention is when you choose XYZ axis, it should be Z, X, if you cross product, it should go in Y direction. So your Y direction should be inside. So that mg, torque of mg is inside, so it is in plus Y direction. But torque of F2 and F4, see once again, this is F2 here, position vector is R, this is the position vector direction, R direction, and this is that F2 direction. R cross F2 is coming out of the board, so it is in minus Y direction. So you have minus here. Similarly for F4 you have minus. Okay. Let me take some more examples of equilibrium. Equilibrium itself is a beautiful phenomena to analyze. Who will come? You will come. All these corner seats are vulnerable. You have to hold this pen in your hand with minimum points of contact. Of course, you can hold it at the center of mass, just one point of contact, but apart from that, okay, you have to just keep it horizontal, just hold it, nothing else, but not like this, so that there are 10,000 points of contacts, right? Minimum area of contact with your fingers, one finger, two fingers, three fingers, whatever. Keep it horizontal. You have to keep it horizontal. Good. So minimum, how many contacts you need?
Still it is more than 2.
Okay, small area I will take as 1.
2 points,
Minimum 2 points, right? Okay. You can see it. This is the way you can hold it. You have to press from the up, you have to press from the down. Why? The weight is only downward. I should apply only upward force. Why am I also applying a downward force?
So you can pivot it this way because you are not on the center of mass.
Otherwise it will rotate. And so one finger is up, one finger is down. Right? The upper finger is pressing it down, the lower finger is pressing it up. So I am applying an upward force, I am applying a downward force. From the thumb I am applying a force in downward direction, very good. And from this forefinger I am applying a force in, which of these two is larger?
The lower one.
The lower finger.
Lower one.
The lower finger, yes. because the 3 force set should add to 0. Mg is also downward, and the thumb is also pressing it down, and my forefinger has to balance both of them. Okay, so that upward force by the finger is more, the downward force by the finger is less, and the difference is equal to that mg. That takes care of translational equilibrium. Now the rotational equilibrium, why it is not rotating, how it is in rotational equilibrium? You have to take the total external torque, and that should be 0, and see how it is 0. This is the situation. You are pressing the pen using this thumb, that is downward, and then using this finger you are pressing it upward, and the weight. So the downward force F1 by the thumb, the downward force mg by the gravity, these two will act together to balance this F2. So what can you write? F1 plus mg equal to F2. So that takes care of translational equilibrium. It is not going up, it is not going down. Now come to torque. Where do you want to take torque? Any point I can choose and take torques about that. Total external torque should be 0. So take this point. Okay, take this point, this central point, and torque of all the forces about this. Torque of mg will be 0, then torque of F1. So let us take this distance as x1. So what is the torque of this F1? This is the origin here. So the position vector of the point where this force is applied is in this direction. This direction. This is the position vector r. Position vector r is this. This is position vector r for this point. So the direction of r is this. R cross F. Remember, torque is r cross F. So r is this, and F is downward. So downward. So this is F. What is the direction of r cross F? R cross F. Anti-clockwise, coming towards us. So anti-clockwise. And what is the magnitude? Magnitude will be F1 into this x1. So x1 into F1. So this is the magnitude, and that is the direction. Right? R cross F, R and F are perpendicular. So RF sine theta, and R magnitude is x1, and this F magnitude is F1. So it is this. Now come to F2. So let us take this distance as x2. This distance as x2 from the center to the point where the force is exerted. So at this point. So now r vector is this. Here is the r vector, and force is upward. So r is in this direction and force is upward. So what is r cross F? The direction. First look at the direction. R is towards left and force F2 is upwards. So this is r and this is F2. So r cross F is clockwise going into. So it is clockwise. As seen from our side, it is clockwise. And what is the magnitude? This time it is x2 into F2. F2 is this force and x2 is this distance. Right? Now for rotational equilibrium, these two magnitudes should be equal. The directions are already opposite. One is anti-clockwise, one is clockwise. So these two should be equal. So x1 F1 should be equal to x2 F2. So now you have two equations, F1 plus mg equal to F2, x1 F1 equal to x2 F2. So from these two equations, you can find F1 and F2. Other things are known. What are the other things? X1. What is X1? Distance of this F1 from the center. So where I am applying the downward force where I am putting my thumb, that one can measure that distance. Then x2 where I am applying upward force, distance of center from there, that is x2, that one can measure. And mg, the weight of the pen, right? You can just weigh it, how many grams. So mg you know in newtons. You can measure x1 and x2 where you are putting your thumb and your finger in centimeters, convert it to meters. Use these equations, you get how many newtons you are applying from your thumb and how many newtons you are applying from the finger. Now one more problem on this equilibrium, I think we will stop there. Look at this duster. Okay. Now I am keeping it here by applying a force perpendicular to the surface of this duster, right? Now only look at the duster. I am not concerned what happens to my finger, what happens to the board, what happens to the earth. Duster is the rigid body I am talking of. Now you have to see how it is in translational equilibrium and how it is in rotational equilibrium. If I draw a diagram for this, the diagram will be something like this. You have a wall, this is the board surface I am representing. Then you have this duster, and then I am pushing it perpendicularly, a force F I am applying here. This is the physical situation, actual situation, and this is the diagram for that. Okay. Now tell me, what are the external forces on the duster? Yes. So mg, I draw it from the center. So mg. Friction. Where? Friction. Can someone draw? My hands are already dirty. Can you draw? Draw friction. Oh, there. Who exerts friction? What object exerts friction? Huh? Small f, right? Small f for friction, small f, right? Okay. See, friction is by the surface on which the duster is trying to slip, right? The duster is in contact with this whiteboard surface. So that whiteboard surface is exerting force on the duster, and that will exert right at the contact surface of this duster. It is on the duster, but the surface of the duster, not middle. There is no contact there. And this duster surface also exerts a frictional force on the board surface, but I am least concerned about that. What happens to the board is not my business. Okay. Duster is also exerting a force on the board surface, and that will be downward. These are action reaction pairs. On the duster, by the board, up. On the board surface, by the duster, down. They are action reaction pair, but I am not concerned about that other one. So friction is here. What else? Can you draw that normal reaction, or you want to draw? No? Okay, good. Now you have drawn it slightly above the center. Let's analyze. Let's take it and analyze. Now for vertical equilibrium, what should be our equation? mg is equal to small f, right? Good. So in vertical direction, all the forces should add to 0. So F is equal to, small f is equal to mg. In horizontal direction, all the forces should add to 0. What does that tell? Capital F is equal to, now let us take torque about some point, whatever point you choose. Which point? Which point I take as origin? You tell me, whatever point you wish. Center of mass, okay, fine. So let us take the center of mass. Torque of mg equal to 0. Why? It's right at the origin. The r vector itself is 0. R vector is the vector from the origin to the point where the force is acting. And this force is right at the origin itself. So R vector is 0. So this is 0. Now torque of N about this origin here. So R vector is this one. This is R vector. This is R vector actually. This is the direction of R vector, right? From the origin to the point where the force is acting, that is R vector. Okay. So if this is R vector, which is in this direction, this is N vector, what will be the direction of R cross F? Coming towards us, right? Coming towards us. Or if I talk in terms of clockwise, anti-clockwise, how it will try to rotate? Anti-clockwise. So torque of N is anti-clockwise. Then F, torque of capital F. What did I write? Torque of mg is 0, torque of N I have written, there are two more. Torque of F. Torque of F, so remember the physical situation. This is F, capital F, and the origin is at the center of the duster. So what is the torque? 0. R vector and F vector are along the same line. This is origin and this is the point. So this is R vector. I am right at the center. Okay. So this is R vector, this is F vector. So this is 0. Then what is left? Small f, friction. Now this is the direction of R vector. This is actually R vector, this is R vector, and this is F vector. What is the direction towards us? Clockwise or anti-clockwise? The total torque cannot be 0 in this situation. Both the torques are anti-clockwise and the remaining two torques are 0. So total torque has to be 0. It is in rotational equilibrium, see. It is in equilibrium. So total torque must be 0. So somewhere this picture is wrong. What should I do? I have to shift the normal reaction. Friction I cannot do anything. Friction will be applied only where the surfaces are in contact. Gravity I cannot do anything, that will be from the center of mass. Capital F I had already committed, I am applying at the center and perpendicular to the surface. It is only the normal force. Okay, so this normal force is not from here. I am pushing it here, friction is here, mg is here, and the normal force must be like this. It shifts down, so that now the torque of this N is clockwise and torque of this friction is anti-clockwise, and they balance each other, and the total torque is 0. Okay, right? So that is how the equilibrium is analyzed. So I think I have done many things like that. I'll just do this demonstration and leave it to you to analyze. This is a cycle wheel, and there's a cloth tied to it, this right hand I will be leaving, what will happen to this disc? It will tilt. Why? Is this a rotation? Where is the axis of rotation? It's going in these circles, right? So the axis of rotation is this way. It is at rest. I am just leaving at this instant, just after leaving. Okay, the angular velocity is 0. It is at rest, and after that it picks up an angular velocity, and the direction of angular velocity is this way. So there must be some torque. If it is picking up angular velocity, that means there is an angular acceleration. So there must be a torque. Where are the external forces? I have left this right hand, remember. Where are the external forces? String upward, gravity downward. Correct? Now where do I take the torque? At the center or at this point, wherever you say. What is the center? Everyone likes center. Okay, so the torque of mg will be 0. Because torque is, the force is applied at the origin itself. But then this T, this tension, this force by this string, force by this cloth, that is here. Tell me where the force is applied. Put the finger. Right, put the finger where it is applied.
Yeah. So it's applied upwards from there.
No, but my system is this wheel.
Yeah.
So that external force has to be on some point of this wheel.
It's applied on this point.
Correct. On this point, right? So where is the position vector r? Put your pen. Right, very good. Put your pen. What is the direction of? Yeah, you put your pen in the direction of r. This is r. You just put it there. So now you can see the position vector r. You can see the force which is upward. Tell me where is r cross f? What direction? Towards you. That means this is the direction of torque. And see, it picks up angular velocity in this direction. If it is going this way, from your side it is anticlockwise. The angular velocity is towards you. From 0 angular velocity it is picking up angular velocity in your direction. Perfectly normal. Your torque was in this horizontal direction towards you. And this torque produced this angular acceleration, and angular velocity was picked up in the same direction. Right? So this simple falling of this can be taken as a good example of doing all this analysis of torque and direction of the torque, r cross f, angular velocity direction, angular acceleration. Everything is there in just falling this from this way to that way. Now I am now doing something else. See what happens.
Slowly.
See what happens. It's not just falling. It's still remaining vertical. But then it is rotating. What is the direction of this rotation? From seen, as seen from the top. Correct? So if it is going this way, there should be some torque in this direction. Something should be there which is doing something. Okay? But it's not that. Not that, because the tension is vertically upward. R cross F cannot have vertical component. R cross F has to be perpendicular to F. F is vertical. R cross F has to be perpendicular to F, must be horizontal. mg downward, no other force. No. Tell me the forces. What are the forces on this wheel when it is rotating, moving, whatever? What are the forces on the wheel? One is this tension, one is this gravity. Any other? But that was a history. No, that doesn't is not maintained. Once I left it, I gave a torque. Okay, that is also a good example. it was at rest. There was no angular velocity. And then I did something and it picked up a velocity. Right? Zero angular velocity, it picked up an angular velocity. During the period I was in contact, I was exerting a force tangentially. During that period, it picked up a velocity. Now, let's analyze that. What is the direction of that angular velocity? Now, I had applied a force in this tangential direction. Okay, so this is F, this is R. What is R cross F? Towards you. This is R vector. I am applying it from here. So this is R vector. And my force is in this direction. So this is F vector. R and F, R cross F towards you. The torque is towards you, and see that it is picking up velocity towards you. Right? So that torque is equal to I alpha and all those things is there in this action also. But what I am doing now, what I am asking, after I have left, now I am not applying any torque, any force. After I have left, say, at this time, the only forces are by that cloth which is upward, by gravity which is downward, and none of that can give you a torque in vertical direction. And so none of these can give you a rotation in a horizontal plane. Yeah. Who exerts that force? Motion is not a common or proper noun, is an abstract noun. The forces are exerted by particles. The forces are exerted by fields. Motion cannot exert a force. Force is exerted by string, force is exerted by spring, force is exerted by earth, force is exerted by sun, a magnet, a charge. Force is not exerted by velocity, force is not exerted by motion, force is not exerted by my feelings. Okay. All right, so I'll just give a small hint and I'll close it here. See, when I just left it from here, the angular momentum was 0 to start with, correct? And therefore, when I applied a torque which is dl by dt, so dl should be equal to torque into dt, right? This is the equation. So a change in angular momentum should be in the direction of torque, correct? dl vector is equal to torque vector into dt. Since the initial angular momentum is 0, no motion, so that dl has to be in the direction of torque, and therefore you saw that okay, it picked up this velocity in the direction of the torque itself. But when I rotate it, there's already an angular momentum in this direction. There is already an angular momentum in this direction, correct? And the torque, what was the direction of torque? So dl is in this direction. Yes, if the initial angular momentum is 0, the final angular momentum, that means after time dt, is also in this direction. But now initial angular momentum is in this direction, and the change, that dl is in this direction. So you have L here and dl here. So what is the final angular momentum after dl, after time dt? It just turns. You have L vector horizontal pointing towards that door. You have dl vector pointing towards that back door. dl is small. Why it is in this direction? Because torque is in this direction. Right? See, this is the force and this is the r vector. So r and cross f, so that is in this direction. So dl vector is in this direction, but L vector is in that direction. I have already given a spin. Seen from this side, it is anti-clockwise. So L is here and a small dl is here, both are horizontal. When you make a vector addition to find the final angular momentum after time dt, you will just turn. The torque of this force, right? Because when I do it and I just hang it, this force is there, okay? This r vector is there, this force is there, so r cross f is there, and that r cross f has a direction towards you, and that if you have a torque, you must have dl. dl must be equal to torque into dt, and they should be in the same direction. dl and torque should be in the same direction. So since the torque is in this direction, dl is in this direction. Initial L was here, you add this dl, then you get a new L which is slightly rotated. But if the angular momentum has to this way, then your direction should be perpendicular to that. Then only you have angular momentum in this direction. So it keeps moving in this fashion. Yes. That's right, because dt is small, so it slowly rotates. That is a good question. I am doing it that way. What if I do it this way? But you know that it is, for me it is easier to do this way. Now my hand, if I take it that way, I cannot exert a lot of force. Perhaps you can do that, you are on the other side. Give it a spin, right. Right. Okay, give a lot of spin. Sure. Good. Oh, sorry. 1 second. No, wait. Hold it here. Okay. Good. So it is rotating the other way. Your initial angular momentum was now this way. dl is still that way, so L plus dl will go that way, so it rotates. How?
Because sir, he's holding it like that.
This is the force, remember, there is a force. This force has a torque. And once you have a torque, see what is written there. dl is equal to torque into dt. And they are vectors, so the direction of dl is same as the direction of this torque. So you see what is the direction of r cross f. That is the direction of dl. You see what is the initial direction of L and add the dl to that. That will give you the final. I will just give an analogy before closing. If I drop this, this velocity is 0. The force is in vertical direction. So the final velocity is also in vertical direction. But if I project it, the force is vertical direction. But after a time dt, the velocity is not in vertical direction. It only slightly turns. There was a velocity. That dv is still downward. Force is equal to dv by dt. That dv is f into dt. F is downward, dv is downward. But originally there was a horizontal v. Add a small dv there, it just turns. The final velocity is not vertical. But if the initial velocity is 0, yes, the final velocity is also vertical. That is what is exactly happening here also. If the initial angular momentum is 0, that dl decides the final direction of the angular momentum. But if there is already an initial momentum and you are adding dl to it, then you have to see how that is adding to it vectorially, and then you can decide what is the direction of L by L plus dl. Okay, thank you very much. I hope I have given you some qualitative feeling at least of all this rotational dynamics and the parameters which are coming into that, and the details of course you will learn in your own regular classes. Okay.